Hello guys, so today we are going to discuss another sorting algorithm, that is bubble sort, right? So what bubble sort says that if you are given any unsorted sequence of integers, so what bubble sort algorithm will do, it will just try to bubble up the largest possible number in the whole unsorted sequence, right? So here you can see that currently in this unsorted sequence 5 is going to be the largest number. So what bubble sort will do, bubble sort will try to just place this largest number from the unsorted sequence to its best possible position, right? So it will just place it to the best possible position. So what bubble sort will ensure that after each iteration, whatever the unsorted part is left, we will just make sure that the maximum of that unsorted part is going towards its best possible position after every iteration, right? So it will just bubble up, it will just try to make sure that these integers are getting bubble up to the best possible positions in the sorted sequence, right? So let's see what is the basic intuition behind bubble sort, right? So suppose that you are given any unsorted sequence. Suppose you have an unsorted part from a sequence. Suppose this is a1 a2 till the position am, and after that if you start from am plus 1 am plus 2 till an, which is a sorted part. So this is a sorted region and this is the unsorted region. So what we are going to do, we will just make sure that inside this sorted part, this is going to be the minimum element, right? Inside this sorted part, this is going to be the minimum element, and say inside this unsorted part we have some element x as the maximum element, right? So what we will try to ensure that after each iteration, whatever the division is, we will make sure that this minimum element of this sorted part is every time greater than the maximum element of this unsorted part, right? And what we are going to do at each iteration, we will just pick out this maximum element and put it to its best position. So if this maximum element is just smaller than this minimum element of the sorted part, then what will be the best possible position after the whole sequence is sorted for this maximum element? It will be just behind this am plus 1 element. So we will try to just place x here, right? So at each iteration we will just divide our array into two parts. In the initial iterations, the whole array will be considered as the unsorted part and the size of the sorted part will be 0. And after the complete sorting algorithm has been executed, this sorted part will be equal to the size of the array and the size of the unsorted part will become equals to 0, right? So let us just see how a basic dry run and see that how we can just apply bubble sort in the following case, right? So suppose the array given to you is 5, 4, 3, 2, 1. So here you can see that this array is arranged in the descending order. So if it is 5, 4, 3, 2, 1, right? So at each iteration, what we are going to do, we will just keep a tracker I as well as a tracker j, right? We will just keep a tracker j. So now what we are ensuring that if the current element which I is pointing, if it is greater than the just next adjacent element, then we will just swap these two elements, right? So here you can see 5 and 4 will be swapped and 4 will come here, 5 will come here, right? Now I will be incremented. Let's say just we are just keeping things on a simpler note by keeping just I as our variable. Now I is pointing to 5. Now I will be compared with I plus 1th index, and here you can see that 5 is greater than 3. So again we will just swap things from here to here. So here you can see this is 3 and this is 5. Now again 5 will be compared with 2, and here you can see it will again be swapped. So 2 will come here, 5 will come here. After that 5 will be swapped with 1. So this will be like this sequence, right? Now again we will just start I from the very 0th index, that is this one, and now here you can see when 4 and 3 will be compared, 4 will be greater than 3, so we will just swap 4 and 3, right? So 4 and 3 will be swapped and 3 will come here and 4 will come here. Again 4 and 2 will be swapped, so 2 will come here and 4 will be swapped to here, and again 4 and 1 will be swapped, so these two come here. So again here you can see that we just picked out 4 as the maximum element from the unsorted part, and we just placed 4 at its best position. So at each iteration at least one of the element is getting placed at its best possible position. Now if you compare 3, so here you can see we will start again from I is equals to 0. We will compare I with the next corresponding element. So here you can see 3 and 2 will be compared. So 2 will come here and 3 will come here. Again 3 and 1 will be swapped. So here you can see 3 and 1 are going to be swapped. So 1 comes here and 3 comes here. And now if we just compare 3 and 4, so no swapping will occur because 3 is lesser than 4. Now at last what will happen is we will just compare 2 and 1. So 1 will come here, 2 will come here. 2 is also present at its best position, and at last 1 is also present at its best position. So here you can see that we just at every iteration we were just bubbling up the maximum possible element from the unsorted sequence, and we just place this bubble to the sorted part, right? And at last the size of this sorted part will grow up till the size of the original array, right? So let us just see that how we can just implement this algorithm. So what we are supposed to do, we can just try to mimic the same algorithm in the code. Like we will just have one pointer which will be pointing to the first position, right? And what we can say is we can just have a variable which can just keep a track on the fact that if we are sometimes swapping an element or not, right? So here you can see when 5 was present here and 4 was present here, you can see that when we were just swapping both the elements, we know that swapping will occur only in those times when the some part of the array is unsorted, right? But if the whole array is already sorted, then obviously no swapping will occur. So we can just keep a variable that can just track the fact that if we are swapping some element or not. And if in the whole iteration, if we are not doing any kind of swapping, then obviously the whole sequence is sorted and there is no point of reiterating to the whole sequence again and again, right? So let us just try to think in this manner only. So we will just keep a track on a flag. That is, suppose we are keeping a flag track on the done flag. So initially what we can suppose is this done flag is marked as what? False, right? And what we can do is while this flag is false, right? While this flag is false, we will just try to implement the algorithm. Now what the algorithm will say, suppose at each iteration I will mark this flag as true, right? I will mark this flag as true, and if at any time any swapping will occur, I will just change the flag to false again and the loop will be implemented again, right? Now we will start from I is equals to 0, and what we can do is while I is less than n minus 1, right? We will just go till the last index and we will just check that if array at I is greater than array at I plus 1, then what we can do is we can just swap the element present at the ith index with the element present at the I plus 1th index. And as I said that if any one swapping is also occurring, then also we are at an unsorted sequence and we are supposed to sort the sequence. So we will just again mark this done variable as false, right? We will just mark this as false. We will just close this if loop if conditional and increment the value of I, right? So here you can see that as soon as we will just come at this while loop, we will just check that if we are greater than our adjacent element, and if that is the case, then we will just swap myself and just change the variable of the done flag, right? So here you can see that if the sequence is already sorted, suppose that sequence is like 1 2 3 4, so here you can see that the sequence is already sorted. We will start with the done variable as false. We will check that while not done, that is while the value of done is false, we will mark the value of done as true. So we will just mark the value of done as true, right? We will start the variable I is equals to 0. We will check that while I is less than n minus 1, we will check if I is greater than the adjacent element. So here you can see 1 is not greater than the adjacent element. So this if conditional will not be executed. I will be incremented. Now I will become equal to 1. So 2 will be compared to 3. Again, no if conditional check will execute. Now I will become 2. 3 is not greater than 4. 3 is lesser than 4. So again, this conditional will not be executed and we will just come out to the while loop. Now here you can see that after we just came out to the while loop, the value of this done variable is true. So if we will just try to reiterate in this corresponding while loop, then obviously this while loop will terminate. This while loop will terminate as soon as we have got our whole array as sorted. So what happens in the case of bubble sort is if the array is already sorted, right? So no swapping generally occurs and we can just in linear time check that the whole array is getting sorted. But in the worst case, what can happen is we can get an unsorted kind of sequence, and in this unsorted kind of sequence, every time we are starting from this very first index and going till the last index, right? We can even optimize this approach by not iterating till the last index. Why? Because we know that at the first iteration, the largest number will be present at its best possible position, that is last. After the second iteration, the second largest number will be present at its best position, that is second last, and so on. So we can just reduce the searching part, the searching space at every corresponding iteration. But let us say that in the worst case, we are just iterating to all the n sequences. So the number of iteration will lead to the complexity of big O of n square in asymptotic notation. While in the best case, this is going to be a linear kind of scenario. In the best case, the bubble sort algorithm will run in linear time, that is big O of n, right? So I hope the logic for the bubble sort algorithm is clear to you all. This is one of the very fundamental algorithm in sorting algorithms, and this will lay down the concepts of more sorting algorithm for you guys, right? So I hope you like the lecture, and if you have any suggestion, you can just put them down in the comment section. We will meet in the next video. So thank you guys. See you next time. Hello guys. So today we are going to discuss one of the very important sorting algorithm, that is selection sort, right? So let us just see what the selection sort algorithm say to sort an unsorted array. Suppose that this is the given unsorted array that we are supposed to sort. So what selection sort says is that at every iterations, what we are going to do is just divide the array into two parts such that one part will be completely sorted and one part will be unsorted. And at every iteration, what we are going to do, from the unsorted array, we are going to find the minimum element and we will place this minimum element at its best position. So let us see how to iterate over this array using the selection sort algorithm. So to implement the selection sort algorithm, what we will do, we will take help of 3 pointers. So let us just name it as I, and we will make one pointer j that will start from I plus 1th position. And we will also take a minimum index pointer, right? So at every iteration of I, what we will say is this minimum index element will be equal to the element pointed by the ith pointer, and then what we will do is just start our iteration in this particular sub array, and we will find that if there exists any element which is smaller than the element present at the minimum index, and as soon as we will be finding more elements which will be lesser than the element pointed by the minimum index, we will just update the minimum index. But for the time being, we will start the iteration saying that the minimum index element is the element pointed by the ith pointer. So here you can see the indexing will be 0, 1, 2, 3, 4, 5 and 6, right? So let's just start. So on the initial node, the I will be pointing to the 0th element and j will be pointing to the I plus 1th element, right? So as I earlier said, in every iteration I will say that the minimum index element is the element pointed by the ith index. So I will mark minimum index element as 0. Now what we will do, we will start the iteration of j from I plus 1th index to the n minus 1th index, and in this sub array we will find the element which is smaller than the element pointed by the minimum index. So now here you can see, is 2 less than the element pointed by the minimum index, which is 17? Yes. So what we will do is just update the value of the minimum index as 1, and what we will do is just increment the value of the j pointer, because there can be more elements which will be still smaller than the element pointed by the minimum index element. Now j is pointing to 1. So is the element pointed by the jth index smaller than the element pointed by the minimum index? And minimum index pointer is pointing to 2. So here you can see j is pointing to much lesser element. So we will again update the value of minimum index as 2. And again j will be incremented, right? So now j will be pointing here, and here you can see 9 is not less than 1 because 1 is pointed by the minimum index. So we will not update the value of the minimum index, and again j will be pointing here. So now here you can see 8 is also not less than the element pointed by the minimum index, which is 1. Again j will be incremented. So here you can see j is pointing to 7, and here you can see 7 is also not less than 1, and at last j will be pointing to 13. J will be pointing to 13, and again 13 is not less than 1. So we will stop the iteration of j, and now as soon as the loop of j will end, what we will have in our hand is the minimum index element and the element at the ith index. What we will do is just swap the elements present at the ith index and the element present at the minimum index element. So now after swapping, 1 will come here and 17 will come here, right? So here you can see we have just placed 1 at its best position. Now we will increment the value of I. I will be pointing here. Again a new fresh loop will start and minimum index will be initially pointing to the same element pointed by the ith index, that is 1, and we will start the jth pointer from I plus 1th index. Now we will compare, is the element pointed by the jth pointer is smaller than the element pointed by the minimum index? So no, j is not smaller than this, so we will just increment the value of j. Now j is pointing to 9. Is 9 less than the element pointed by the minimum index? That is 2. So 9 is not less than 2. Again j will be incremented. Here you can see 8 is also not less than 2. J will be incremented. 7 is also not less than 2. Again j will be incremented. And at last here you can see j is pointing to 13 and 13 is also not less than 2 because 2 is the element pointed by the minimum index. So we will just complete the loop, and here you can see we will again swap the values pointed by the ith pointer and the minimum index pointer, and here you can see the both are pointing to the same element, so the array will be remaining at its original position only, and we will increment the value of I. So here you can see we have also placed 2 at its best position. Now again minimum index will be equal to 2, I will be pointing to 2 and j will start from I plus 1. So again, is 9 less than 17 because 17 is pointed by the minimum index? So again yes, 9 is less than 17, so we will update the value of minimum index, that is 3. Now we will increment the value of j. So j is pointing to 8, minimum index is pointing to 9. Is 8 less than 9? Yes, 8 is less than 9. We will again update the value of minimum index as 4. Now j will be pointing to 7 and minimum index is pointing to 8. So is 7 less than 8? Yes, 7 is less than 8. So again we will update the value of minimum index as 5, and at last j will be pointing to 13, but 13 is not less than 7, so we will do nothing and the loop of j will be completed, and at last what we will do, we will swap the elements pointed by the ith pointer and the minimum index pointer. So here this will be swapped and 7 will come here and 17 will come here, right? So again the loop of I will be incremented. So I will come here, minimum index will start from 3, right, and j will come here, right? So again, is 8 less than 9? Yes, 8 is less than 9, minimum index will be 4. Now j will be pointing to 17. Is 17 less than 8? No, 17 is not less than 8, j will be incremented, and at last j will be at 13, so 13 is also not less than 8. So we have our minimum index pointing at element 8 and I is pointing at 9, so we will swap these elements. So this will become 8 and this will become 9, right? So now I will come here, minimum index will start again from 4. Now j will start from 17. Is 17 less than 9? No, j will be incremented. Is 13 less than 9? No. So j will complete its loop, and again I and minimum index are pointing to the same element, so no swapping will occur. And even if we just swap the element will be at its original position only. So now I is pointing to element index 5, minimum index is also pointing to 5, and j will start from here. Now is 13 less than 17? Yes, 13 is less than 17. We will update the value of j with minimum index with the value of j, that is 6, and j's loop will be completed, and we will swap the element present at the 6th index and the 5th index. So 30 and 17 will be swapped, and here you can see we have completed the sorting of our array. So as soon as I reaches the n-2nd index and completes its procedure, our whole array will be sorted, right? So let us write the pseudo code for the following algorithm. So the pseudo code will be pretty easy for this algorithm. What we will do is just start our loop of I from 0 and iterate I till I is less than n-1, that is the instance when I will reach the n-2nd index, right? And we will increment the value of I. We will keep a minimum index pointer starting from the value of I at every iteration, and then we will start a loop of j starting from I plus 1. J will go up to j less than n and j plus plus. Then what we will do, we will compare that if array at minimum index is greater than array at j, we will update the value of minimum index. So here you can see minimum index will become equals to j, right? And as soon as the for loop of j will be completed, we will just swap the values of the ith index as well as the minimum index. So by following this particular algorithm, you will be able to implement the selection sort algorithm. So here you can see the selection sort algorithm is pretty easy to implement. And talking about the time complexity of the selection sort algorithm, so here you can see that starting from the very first index, we are initially making n minus 1 iterations, then n minus 2 iterations, and so on, right? Till the time when we will do just one iteration. So the sum of these terms will be n into n minus 1 by 2, and in asymptotic big O notation, this will lead to big O of n square time complexity, right? So selection sort has a very intuitive and a very simple algorithm, right? And it has a very important application also in modern computer science, because suppose that you have a lot of data in your hard disk, right? And you have to just sort that data. So here you can see the swapping procedure is occurring very lesser number of time as compared to the other algorithms of sorting. So the conditions where you have to minimize the number of swaps and still you have to just sort the array, selection sort can perform way better than other algorithms, right? So I hope the logic for the selection sort algorithm is clear to you all. So whenever there is a condition that as I explained in the earlier example, that there are a lot of data in your disk and you have to do some sorting kind of thing, so there is a condition that you have to minimize the swap, then selection sort algorithm can perform way better, right? So I hope you like the video, and we will be continuing our series on this sorting algorithm videos, and we will be uploading more videos on these algorithms, as well as if you have some specific topics that you wish that we should teach in our YouTube channel, so please comment down in the comment section, and if you like the video then please hit the like button. We will meet you in the next video. So thank you guys, see you next time.